OCR Chemistry A 5.2.2 Enthalpy and Entropy. Using Chemistry Explained needs your active participation. You need to write notes and complete the tasks either with pen on paper or on a tablet. Control the pace of the lesson by pausing or replaying the slides. Most important, when prompted, pause the lesson, complete the task, thinking the problem through, which means taking your time. When you're ready, continue the lesson, correcting your work. So we will start with a general idea of the concept of entropy, look at entropy change, how to calculate entropy change, a new idea, Gibbs free energy, then how to calculate involving Gibbs free energy change, and then a final roundup on the concept of stability. Entropy is a new idea. It's given the symbol capital S, and it's a measure of the degree of disorder in a system. A system with high disorder has high entropy, an ordered system has low entropy. But we need to think about what we mean by disorder. A system with more possible ways of arranging its particles is more disordered. So a system with very few ways of arranging the particles, alternative ways of arranging the particles, is ordered and has low entropy. Now in physics, you'll probably, if you are learning physics, you'll meet it defined as dispersal of energy in a system. The more spread out the energy, the greater the entropy. Now that is not that useful at the first treatment in chemistry. The most useful and productive way of defining entropy or thinking about entropy is as a degree of disorder in a system. The units of standard molar entropy, which is given the symbol capital S standard sign, are joules per Kelvin per mole. So if we use our simple particle model of solids, liquids and gases, we can see that there are very different degrees of disorder. You'll be used to seeing solids represented as regular and close arrangements of particles, which obviously have high order. A liquid, there is some degree of disorder, and a gas, a random arrangement or highly disordered. So in terms of molar or standard molar entropy, solids have a much lower entropy than liquids, which have a lower entropy than gases. This is borne out by reference to data books where there are tables of standard molar entropies. That for solid water is plus 40. The standard molar entropy for liquid water is plus 70, and the standard molar entropy for gaseous water plus 189. So quite clear that the solids have much lower entropy than liquids, which have much lower entropy than gases. So moving on to qualitative ideas of entropy change, delta S. One of the main uses of entropy or entropy change is to predict the direction of change in a system. Consider these spontaneous changes. These are changes that occur without an input of energy. The evaporation of water from a wet towel. So here liquid water is forming into the vapor. The spreading of a crystal of potassium permanganate or potassium manganate 7 in a beaker of water. Here a highly organized crystal of potassium manganate 7 forms a disordered aqueous arrangement. The jumbling of matchsticks when a box of matches is empty on a tabletop. It's a chemistry teacher's favourite demo. Obviously, we've got ordered to relatively disordered. All of these spontaneous processes involve an increase in disorder, in other words, an increase in entropy. As a very simple introduction, we are going to say that an increase in disorder, a positive delta S value, indicates that the process will occur spontaneously. That is, once started, it will continue to run without an extra input of energy. If we look at some chemical changes, we can see some key characteristics that will enable us to identify the entropy change. So reactions with more product particles than reactant cause an increase in entropy. We've got more ways of arranging more particles. So if we look at the decomposition of calcium carbonate, for instance, we'll take 1 mole of calcium carbonate, we'll achieve 1 mole of calcium oxide and 1 mole of carbon dioxide. So we've got twice as many moles on the right-hand side on the product side. So that would indicate that there are more ways of arranging those particles. Therefore, there's more disorder on the product side. Therefore, that's an increase in entropy. Now, we can also look at reactions with more product gases than reactants. So if we look at the decomposition of ammonia to form 2 moles of ammonia to form 1 mole of nitrogen and 3 moles of hydrogen, all in the gaseous state, then we have got 2 moles of gas on the reactant side and 4 moles of gas on the product side as written. So that, of course, means we have an increase in entropy, a positive delta S value. We can also look at systems where a change in state occurs. For instance, freezing of water liquid turning into water solid. Well, we know from earlier in the lesson that liquids have a higher entropy than solids, so here we would say that we've got a negative delta S value. So here are some problems. Predict whether the entropy of the system will increase or decrease for the 5 reactions as written, in other words, the 5 systems. Pause, come back to check against my ideas when you are ready. Okay, so A, that will be an increase. We're making a gas, that's crucial. We're starting with a solid, making a gas, so that will definitely produce an increase in entropy. B, again, that will be an increase. Again, we're forming a gas. We're starting with 2 moles and ending up with 3. So again, clearly an increase in entropy as we go left to right. C, that will be a decrease. We're starting with 2 gases and ending up with a solid. So that will be a decrease in entropy. D, that will also be a decrease because we've got 3 moles on the left-hand side and only 2 moles on the right-hand side. They're all gases, so the numbers of moles would be the key factor. And then finally, we've got 1 mole of gas on the left-hand side, a solid, and then 2 moles of gas on the right. So that would be an increase. So that's called a qualitative analysis of entropy change. So we're now going to look at how to calculate entropy change using standard molar entropies. Provided we have a source of standard molar entropies, we can calculate the entropy change for a system. Very often in exams they're provided for you. If you're not in exams, you might use a data book. So we have here the standard molar entropy for solid calcium carbonate, for calcium oxide as a solid, and for gaseous carbon dioxide. Just as a side point, you'll see, of course, that the molar entropy for carbon dioxide as a gas is much higher than the other two. Now, these values are obtained from calculations, but our starting point would be that the entropy of perfect crystals at 0 Kelvin, minus 273 Celsius, is taken to be 0. So at standard conditions, 25 Celsius, carbon dioxide is calculated to have a standard molar entropy of plus 213.6. As A-level chemists, we do not have to concern ourselves with that calculation. We just use the data. So if I look at a model calculation, I've got calcium carbonate as my reactant and calcium oxide and carbon dioxide as my products. The change in entropy is going to be the final state minus the initial state. So my final state is the molar entropy for calcium oxide and for carbon dioxide. So I sum those two and I take away the initial state, which of course is the reactant entropy. So that's the standard molar entropy for calcium carbonate as a solid. Comes out as plus 160.4 joules per Kelvin per mole. So let me give you a problem. Here is some data. Here is a system, magnesium reacting with copper oxide to make magnesium oxide and copper. Can you calculate the entropy change for the reaction? Pause, come back to check against my workings when you are ready. Okay, so I'm going to reveal my ideas. Again, I'm saying the change in entropy is the final state minus the initial state. So my final state is the entropy of magnesium oxide, 26.9 plus 26.9, and the entropy of solid copper, 33.2. My initial state, the entropy of solid magnesium and of copper oxide. Simple arithmetic gives me minus 15.2. So there's a negative change. There's a decrease in entropy as we go left to right. Now we could not have told that by qualitative inspection. The numbers of moles are the same left and right. We have no reason to suppose qualitatively that there's a decrease in entropy. The calculation allows us to see that. So if you have access to the OCR endorsed textbook, I would recommend that you turn to page 364 and do summary questions 1, 2 and 3 and check your ideas against the answers on page 579. Gibbs free energy. Gibbs free energy is given the symbol capital G. Now if we consider the decomposition of calcium carbonate into calcium oxide and carbon dioxide, we saw earlier that the entropy change is calculated to be plus 160, and we would anticipate a positive change as we're forming a gas from a solid. But using the standard molar entropies, we found it was plus 160. So that would predict that the reaction would occur spontaneously at standard conditions. However, we know that that reaction does not take place at room temperature. If you put a marble chip on the table in the chemistry lab, it will not decompose to calcium oxide and carbon dioxide. It has to be heated. So Gibbs came up with a better way of predicting reaction feasibility by considering both the entropy change of the system, as we've just been doing on the earlier slides, and considering the energy transferred to the surroundings, delta H. And he formulated an equation for the change in what he called free energy, but has now been called Gibbs free energy, delta G. He deduced, or his work showed, that delta G was equal to delta H, the change in enthalpy, minus T delta S, minus the temperature in Kelvin times the entropy change in the system. Now that equation is not provided for you in the data sheets. You're expected to recall it. Recalling it alone will get you 1 mark in general. For a reaction to be energetically feasible, delta G must be negative. So Gibbs combined the entropy change of a system with the energy exchange or transfer to the surroundings, formulated the equation delta G equals delta H minus T delta S. You have to recall that, but you also have to recall that for a reaction to occur, to be energetically feasible, delta G must be negative. And we'll carry out some calculations that will make that much clearer how that works. You're now ready to move on to calculations of delta G. So let me take you through a model calculation. Calculate the change in Gibbs free energy for the decomposition of calcium carbonate at 298 Kelvin. So I need the equation to start with. I'm supplied with the enthalpy change, delta H equals plus 178, and I'm supplied with the entropy change on this occasion. I'm going to recall and use delta G equals delta H minus T delta S. So I now write delta G equals plus 178,000 minus 298 times 160.4. Now where do those numbers come from? Most obviously the temperature is in Kelvin. So 298. In some A-level questions you might be expected to convert from Celsius, but 298 plus 160.4. Well, plus 160.4 is in joules. I must have delta H and delta S in the same units of energy. So normally delta H is supplied in kilojoules. So I'm converting 178 kilojoules so that I have the same energy in the same units. So I've now got here delta H as plus 178,000 joules. If I then use 160.4, because 160.4 is in joules, 178 is in kilojoules, so I must convert that to plus 178,000. Do the math, as they say, it comes out as plus 130,000 joules per mole, but we usually present our answer in kilojoules, so plus 130 kilojoules per mole. Now what can we conclude about that? Well, delta G is positive, so the reaction will not take place at standard conditions. So we've got a definitive prediction. Calcium carbonate will not decompose to calcium oxide and carbon dioxide at 25 Celsius at room temperature. Delta G is found to be plus 130. It is positive. if you recall, for a reaction to be feasible, delta G must have a negative value, so the reaction will not take place. So we know from the previous slide that the decomposition of calcium carbonate is not energetically feasible at standard conditions. However, we also know from common experience that if we heat calcium carbonate over a Bunsen, it will decompose. So we need to somehow determine the temperature at which calcium carbonate will decompose. That is, the decomposition of calcium carbonate becomes energetically feasible. So if we look at the equation delta G equals delta H minus T delta S, we know that as the temperature is raised, this term minus T delta S will become greater. It will become more negative till eventually it becomes greater in magnitude than delta H, and delta G will become negative and the reaction will be feasible. There will be a temperature at which delta G becomes negative. How do we determine that temperature? Well, we know above that temperature the reaction will be feasible because delta G will be negative. Below it, delta G is positive. So at that temperature, we say that delta G is equal to 0, and we say the reaction is at equilibrium. So substituting in the value for delta G as 0, having T as the unknown, delta G equals 0 equals 178,000 minus T delta S, which is 160.4. So we can arithmetically solve for the temperature T, and it comes out as 1110 Kelvin. So the reaction is feasible at temperatures above 1110 Kelvin. At that temperature, delta G equals 0. Below that temperature, delta G is positive and the reaction is not feasible. Above that temperature, delta G is negative and the reaction is feasible. A common question or expectation in OCR Chemistry A exams is the use of comparison to the equation of a straight line, which I will remind you is y equals mx plus c, where m is the gradient and c is the y-intercept. Now, if you look at the equation for the change in Gibbs free energy, delta G equals minus T delta S plus H, delta H. I've slightly rearranged it so that you can more obviously see that the delta H would correspond to the y-intercept, and if we plot delta G being y against temperature in Kelvin as x, then the gradient is going to be minus delta S, negative of the entropy change of the system. So plotting delta G against temperature, we will get a line drawn where the gradient is the negative of the entropy change and the intercept with the y-axis is delta H. If you have access to the OCR endorsed textbook, I recommend you turn to page 369 and answer questions 1, 2 and 3, and then check your answers on those provided on page 579. A final point to discuss is the concept of stability. So we need to consider firstly the idea of kinetic stability and then compare it to thermodynamic stability. So in other words, how fast a reaction may happen versus whether it is energetically feasible. If we look at kinetic stability, for reactions with a very high activation energy, the rate of reaction is infinitely low, and we would describe such reactants as kinetically stable. Thermodynamic stability is determined by whether delta G is negative. If delta G is negative, then that would indicate that a reaction is thermodynamically favoured, energetically favoured. However, a reaction may be thermodynamically feasible but kinetically stable. So, although energetically it is expected that the reaction will proceed spontaneously, the rate at which it happens is infinitely slow. In practice, if we have an infinitely slow rate of reaction, that is kinetic stability, then the reaction is regarded as not occurring. So for my final slide, just the obvious statement that to consolidate you need to practice, you need to find problems from whatever source you have available to you, but those sources which have comprehensive answers are the best. So attempt the problems, check your answers, move on when you are being consistently accurate and complete in your answers. Choose the next topic that you think for you is the one you need to focus on.